After studying this model, you will be able to understand what is a point group, why to classify the molecules into point group, classify the molecules into point groups, various categories of point groups, and examples of type 1 non-axial point group and examples of type 2 single axial point group. From the discussion about symmetry elements present into molecules and operation generated by them, one can recognize the type of symmetry elements present in the molecule. This will help to classify the molecules into various point groups. Applications of physical operation leaves the molecule physically unchanged with similar orientation in the space, and center of mass also remains fixed. Under all symmetry operation, it means all symmetry operation must intersect at a common point which is not shifted by any of the symmetry operations, and such groups are called point group. Why we want to classify the molecules into point group? When there are countless molecules which do not possess any symmetry at all. Though it is true, but many molecules do have local symmetry. Small molecules do have real symmetry. We should understand the behavior of each molecule before we try to understand the larger one. Many of the properties of benzene ring nearly the same whether we are looking at free benzenes or substituted benzenes. Properties of free benzenes are easy to understand since it is difficult every time to look to each and every symmetry elements in molecules and then decide its characteristics. So, it is better to classify the molecules into point group and study point groups. Just like in periodical table, we classify the chemical elements into groups based on their electronic configuration. Similarly, from the presence of the various symmetry elements into the molecule, it can be decided to which point group the molecule is placed. There are two types of notation for naming the point group, that is Schoenflies notation. This notation is used by the spectroscopists and applied to molecular point group. Hermann-Mauguin notation. This is commonly used by crystallographer and groups are called space group. In this module, Schoenflies notation will be used for naming the point group. In chemistry, sometimes same symbol is used to denote both for a point group and symmetry elements. For example, for cyclic CN point group, the generator symmetry element is also represented by CN. One should be very careful while working with such types of point group. It is the symmetry operation that constitute a group and not the symmetry elements. This point has been highlighted earlier also. But classification of molecules can be described in terms of symmetry elements present in the molecule. Each point group can be generated from a smaller set of symmetry operations known as the group generators. Before giving systematic classification of molecule, let us start looking at small number of molecules, that is symmetry elements, and describe the type of group to which the molecule can be placed. It is the combination of symmetry elements, inversion and rotation that give molecular point group in which we are interested in this molecule. The various types of point group categories. These can be divided into 4 categories. Type 1, non-axial point groups or molecules with low symmetry. Second, single axial point group or molecules with intermediate symmetry. Type 3, dihedral point groups or molecules with very high symmetry. that is molecules having n vertical rotation axis perpendicular to the principal axis. Type 4, cubic group, molecules having multiple intersecting higher order rotation axes. Before discussing the scheme of classification of the molecule into point group, let us first take few examples of each category. Example of type 1, that is non-axial point group. Point group belonging to this category are C1, Ci, Cs, and these are low order group where order of the group H is equal to 1 or 2. These do not have Cn axis of any order except C1, that is angle of rotation is 360. Now we discuss these low order groups one by one. Let us first take C1 point group molecules. Molecules belonging to this group have only identity E as the symmetry elements, or we can say that molecules belonging to this category have Cn axis of order 1, that is theta 360. Few examples of molecule belonging to these categories are shown. Let us take few examples. I take this example of a molecule, that is a pyramidal molecules. I am having three different substituents on this, say fluorine, hydrogen and chlorine on this molecule. Do you find any symmetry elements into this molecule? That is, you rotate it, no, it is not a rotation. You take a plane, no, it is not a plane. These and these cannot be reflected. Like this, these and these cannot be reflected. So in this molecule, which is a pyramidal molecule with three different substituents, there is no symmetry elements into this. So this molecule, which does not have any symmetry elements present into this, goes to C1 point group. Let us take another common example of a molecule of this like. That is, four substituents nearly along the four corners of a tetrahedron. I am having this hydrogen, fluorine, bromine and chlorine. Say I am having this. Whether this molecule has any symmetry elements. That is, if I pass this C2 axis, it is not there because this and this cannot be reflected. If I pass this C2 axis, that is this and this cannot be reflected. You can turn down this molecule like this, try to find out any of these sigmas present into this or not. So this molecule does not have any of these symmetry elements, neither plane nor any of the rotation. If I give this rotation, you do not find equivalent positions, that is red and these, they are interchanged. This is not a symmetry operations. So in this molecule also we do not have symmetry elements. Now let us take a system in which I just take this type of molecule over here. Again, this is a pyramidal molecule. Again, I am just taking, let it be sulfur and let it be a double bonded oxygen, and these are fluorine and bromine and chlorine. Again, this is pyramidal molecule. It does not have any of the symmetry element. Suppose you want to pass this C2 axis along this one. These and these are not interchanged. I have different substituents over here. So this is not any of the plane. So this molecule does not have any of the axis or any of the symmetry elements of any type. So these molecules are C1 type molecule. C1 is a trivial point group which contains all the molecules that do not have any symmetry elements in them. In these examples, there is no sigma, there is no I, there is no Cn, only C1 rotation, that is a rotation by 360 degree is possible. So that is only C1 point group. Molecules do not have any symmetry elements. Now there is another point group of lower point group type 1, Ci point group. Molecule belonging to this point group have E identity and center of inversion as the symmetry elements in them. The order of the group is 2, and symmetry elements in these molecules are E and I. Few examples belonging to this point group are shown. These are 1,2-dichloro, 1,2-difluoroethane staggered, P2F4 as shown, 1,3-dichloro, 2,4-dibromocyclobutane, mesotartric acid, 3,5-dimethylpiperazine, and the presence of center of inversion is indicated by the dotted line in between. Here what you find, that is, in some of the examples, center of inversion is lies at the CC bond, that is a bond just like first two examples, or it may be in space, example 3 which are there, or in any substituted type of number 5 molecules like this. So, all these molecules, they have only the center of inversion, no other symmetry elements in present into the molecules. You can try any of these molecules, not then. So, these examples of the molecules belong to CI point group, molecules having only center of inversion, no other symmetry elements present in them. Then we have third of the type 1, CES point group. Molecules belonging to this point group have mirror plane sigma and E as the symmetry elements in them, and the order of the group is 2. Example of the molecules belonging to these point groups are shown, and these are formyl chloride, F2SO, BCl-BrF, NOCl, HOD, and 1-bromonephthalene, CS2ClBr. Like this, number of examples are shown, and in which we just find that is only the one center of inversion is there. Let us take this example. Now, in this molecule, that is, it passes along this, then this and this are reflected and this remains into the axis. So, in this molecule, which is a pyramidal molecule, S double bond O F2, so I am having a C only X, this sigma along this. Like other examples which are shown, you take any of the examples, you will find only one sigma is there. So, all these molecules which have only the sigma in them, they belong to CS point group. All these you can just make a model and you can try that they do not have, these examples do not have any other symmetry element except sigma in them. So, this is the type 1 of molecules which we have taken. Now, example of type 2, that is the single axial point group. Point groups belonging to these categories can CN, CNV, CNH, SN. Now, let us take these 4 types of point group one by one and take few examples which are possible. Let us take CN point group. Molecule in this point group possess only a rotational axis, that is CN axis. No other symmetry element is present in them. These CN generate CN1, CN2, CNN, which is equal to E. Number of, that is n number of symmetry operations are generated by this. The order of the group, that is H, is equal to n. It is a cyclic group and hence it is abelian group. Each operation belongs to separate class. For example, molecule belonging to CN point group are shown, that is H2O2 non-planar configuration. Second example is 1,2-dichloroethane in the given configuration. Third is 1,1-trifluoroethane, neither staggered nor eclipsed. Fourth is cis, COEN twice Cl2, and fifth is BOS3, hydrogens are out of plane of the BO3 moiety and NH2 as shown in the figure. And these are the molecules which have only one rotational axis in them, and that may be of any order which are here. So, these molecules as shown, they belong to the CN point group. No other symmetry elements is present in them. Now, let us take the example of H2O2 or H2S2 as given. I am just taking, this is H2O2, I am just taking over here. Now, if I take these molecules like this, that is these hydrogens and this hydrogen, they are not in the plane, they are outside the plane, just like this. These are out of plane. This is in plane and these are slightly out of plane. So, these hydrogens, they are not in the plane. And this molecule, if I give this type of rotation, this is my C2 rotation. Similarly, the last example C2S2, they have only this type of C2. So, all these molecules which are shown, they have only CN axis of certain orders. Now, CNV point group. Molecules belonging to this point group have CN axis and N sigma V containing CN axis. And few examples belonging to the CNV point group are shown, that is bromine, manganese, CO5, NH3, PF5Cl, Cl is HCl, pyrrole, and other examples can also be cited. Now, here I will just take the case of water molecule, in which I will just take the example of water molecule like this. I will just take simple water molecule and see whether in this we have any axis. Now, in this is my C2 axis, that is both the hydrogens can be interchanged, and it also has sigma V like this and sigma V into the plane. So, this molecule has C2 axis as well as 2 sigma V's into this. That is, CNV point groups are the molecules which have CN axis and sigma V containing my CN axis. This is my CN axis of order 2, and this is one plane and this is another plane. In a pyrrole molecule, it is very similar to the water molecule. It has a 2 sigma V's which are in the plane and perpendicular to the plane and C2 axis. So, in this case we are having now example of CNV. Now, then we have CNH point group. Molecules belonging to this point group have CN axis and sigma H symmetry elements in them. Some examples of these point groups, and these are trans-butadiene planar, BOH3 thrice, all atoms are in plane, trans H2O2, ethylene diamine as shown, 1,4-dibromo, 2,5-dichlorobenzene, trans dichloroethylene as shown, and these symmetry axis as well as plane are shown by this dotted line into this. Now, let us take few examples. I am just taking trans H2O2. It is molecule is like this, and this is your C2 axis, and you can give a rotation around like this, that is like this. This is my C2 axis, and plane perpendicular to this is this, that is my palm which is there. This is plane perpendicular to this and this C2 axis. You can give a rotation like this. So, this molecule has a C2 axis and a sigma H plane into this. So, this molecule has no other symmetry element C2 and sigma H. So, this molecule will go to C2H point group. Now, let us take another example of substituted benzene, that is, I am just taking this, you are as shown in the, you are in this molecule, that is you can take bromochloro, dibromo-dichlorobenzene, and this is the molecule. Now, where you find in this molecule, that is in this molecule, what are this molecule belongs to which point group? That is, if I put this molecule like this and give a rotation about this axis, C2 rotation, by giving C2 rotation about this ball over here, bromine, will be replaced by this. This and this chlorine, that is you give a rotation like this. So, by performing this C2 rotation perpendicular to this plane, I am getting the same configuration, and the plane of the molecule is sigma H, which is perpendicular to this C2 axis. So, this molecule belongs to C2H point group. So, like this, all other examples of these slides can be worked out, and you find that they belong to CNH point group. That is, here in this it is C2H, which I have taken 2 examples for explanation. Now, in this another type, SN point group, if a molecule has CN axis that exist, check for additional S2N axis coinciding with CN axis. If it is there and no other symmetry elements are there, then the molecule belongs to S2N point group. Possible examples are, if S2 is there, it is equivalent to I, S4, S6, S8. That is, S is equal 2 is equal to I, that is Ci. We can express this as follows. If in a molecule there is improper axis of even order, in practice S4, S6, S8 are there, no plane of symmetry or proper axis of rotation except collinear one, whose presence is automatically required by improper axis, then the molecule will belong to Sn, n is equal to 4, 6, 8. The point group Sn, n is equal to even, exclusively consists of the operation generated by Sn axis. Thus, the molecule which have Sn, n is equal to even, are said to belong to Sn point group. The order of the group equals to the number of the operation generated by Sn axis. Examples of molecules belonging to this Sn point group, these are the few of the examples which are shown. First molecule contains S4 axis, second tetraphenyl, this methane contains S4 axis, then this 2378 tetramethyl spiro 44 nonane contains S4, and then this fused ring system contains S6. So, these molecules do not contain any other symmetry elements, so though they belong to Sn point groups. Now, in this module we have learnt define what is a point group, need for classification of the molecules into point group is stressed, classification of the point group is explained, various categories of point groups is mentioned, example of the type 1 non-axial point group C1, Ci, Cs are given and explained with the help of the models. Example of type 2 single axial point group CNV, Cn, CNH, Sn are given and explained wherever possible with the help of the models.